Hi everybody and welcome to this new release webinar, LedaFlow 210. My name is Ludivine Rossvoll and I'm the LedaFlow product owner at Kongsberg Digital. During this webinar, I'm going to present you some of the latest improvements in LedaFlow, first on the models, then on the performance, and finally on the user experience. I will make sure to keep some time at the end to answer your questions. So if you have any questions, please post them in the chat during the presentation, and we will go through them together at the end. I guess that if you're attending today, it is because you know already a bit about LedaFlow, but I have included this slide as a kind of introduction. Let's focus on the application box that is in the middle. As you know, LedaFlow has originally been developed for oil and gas applications. However, we see a growing interest in using it for other types of fluids like CO2 or hydrogen. And due to the good physical models that we have implemented in LedaFlow, the software is very much suited for these new applications. So the reason why I'm bringing this up, it's because I'm going to show you some improvements that are both for oil and gas applications and for CO2 applications. So let's start with the model improvements and the improvements related to CO2 modeling. The reason why we are focusing on this is that LedaFlow is involved in a project called CO2 Flow, which has the ambition to overcome some of the gaps that were identified through a previous project called CO2 Fact. And one of the conclusions from the CO2 Fact project was that the phase change was too slow. So in LedaFlow 210, we have introduced a new phase change model. LedaFlow already included a special mass transfer term that took care of the boiling and condensation, but we have revised that model in LedaFlow 210, and it is now based on a local enthalpy balance for each zone. So what is a zone in LedaFlow? It's a continuous phase, and the phases, the dispersed phases that are included in that continuous phase. So it's either continuous gas plus liquid droplets or continuous liquid and gas bubbles. This enthalpy balance can be used to directly calculate the local phase split according to thermodynamic equilibrium. And this model enables faster phase change. There is less subcooling and superheating. And it also improved the numerical stability, mainly because each zone is sharing the same temperature. So this model doesn't only apply to CO2, it applies to all single component systems. Here is an illustration of the new phase change model and what I mean by a zone. So you have at the top, as you can see, the phase change with the continuous gas with the droplets of liquid. I can use the pointer to point at it here. And the liquid phase with the bubbles of gas. So this phase change is inside a zone, as I said. So it's different from the mechanical mass transfer that is between the continuous liquid phase and droplets and the continuous gas phase and bubbles. So here the gas and liquid zones are treated completely independently. Since the phase change converts continuous to dispersed and vice versa. And that means that there is no interaction with the other zones, and that's what increases the numerical robustness. As I mentioned in the slides presenting the CO2 flow project, the development is either based or validated using the de facto experiments. So you have here a schematic and a picture of the rig that is used for these experiments. We are here specifically interested in vertical downward flow, and we are measuring temperature and pressure. we have a bunch of experiments that are done on this de facto rig. The experiments for pure CO2 are all completed, and we expect the experiments with CO2 with impurities to be completed this summer. So the first graph that you see on this slide that shows some of the de facto experiments. So the first graph shows the average temperature. We can see that there is now a very good match between the measurements that you see, that the square, the black squared on this graph, and LedaFlow 2.10. You can see that it's a much better match than it was in LedaFlow 2.9. I should also mention that the new model keeps the temperature much better on the saturation line while there is a phase change, and that was the motivation to develop this phase change model. There is also a good match in terms of pressure. We don't have any measurement for the holdup, so this graph at the bottom only shows the consequence of this new phase change model and the differences that you can expect between LedaFlow 2.9 and LedaFlow 2.10. When working with single components, we are using what we call the old solver, and the matrix solver that was used to solve the mass was not accurate enough when working with CO2. So we have improved the accuracy by using a higher precision. So this comes at the expense of simulation time, but at least the accuracy is much higher. We have also applied a correction on the gas viscosity and the thermal conductivity for gas like supercritical CO2. This is because the properties for the vanishing phases couldn't be trusted when using the equation of states for the CO2 pure model. And finally, another noteworthy addition that is not necessarily restricted to CO2 modeling, and that I could have placed also in the UX improvements, for example, it's this new API that can be used to integrate with reservoir models. So it is based on the open source Google remote procedure call framework, also known as gRPC, which is a modern framework for connecting processes. And it supports communication between different machines, so it can be used across a computer network. This new API has been used in order to connect LedaFlow together with GEM, the reservoir simulator from CMG. And CMG will release later this year a controller to couple both simulators together. So the reason why I'm mentioning it here, although as I said, it's not restricted to CO2 applications, it's because this has been developed through a GIP that is called Geleco 2. I've put a slide here explaining this, the objective of the project, so which was to develop a controller to manage the interaction between LedaFlow and GEM. And you can have a look at it if you're looking at the video later on. Regarding PVT now, we have now the possibility to use PVT Sim in LedaFlow. So PVT Sim Nova is supported for use in composition tracking cases. This means that composition tracking is not anymore restricted to the use of multi-flash, as long as you have an active license of PVT Sim, of course. Note that we have taken the opportunity to remove GUTS, which is the Ground Unified Thermodynamic Simulator. It was developed through a GIP quite some time ago and had limited functionality. compared to multi-flash and PVT-Sim. So we have decided to remove it from LedaFlow and to keep only multi-flash and PVT-Sim. So if you want to use PVT-Sim in LedaFlow, it's a little bit different than multi-flash. You will first need to work in the PVT-Sim user interface to prepare a PVT-Sim fluid file that has the extension CTM. And then you will import this CTM file in LedaFlow. As soon as it is imported, the information it contains is stored in the database, which means that it is independent from the file itself. There is nothing to configure in LedaFlow. All information will come from the PVT-Sim fluid file. And CalCep has released a new version of PVT-Sim to allow this integration on the same day as we have released LedaFlow 2.10. So please refer to their website if you want to have more information. In LedaFlow 2.10, we have expanded the possibilities for pigging modeling. We have, for instance, introduced a new input called the wax removal efficiency. This is for the user to specify the mass fraction of wax that is scraped off the pipe wall by each pig. This input is, of course, only available if you have activated wax deposition, the wax deposition model. It is now also possible to use the stop simulation controller to terminate a simulation when the pig has arrived at the pig trap. This is quite interesting since we normally don't know how long it will take for the pig to travel from the launcher to the trap. We have made results consistent for normal and bypass pigs. As a result, you may expect a small difference in the results for normal pigs in LedaFlow 2.10. And finally, we have introduced two new outputs, the accumulated mass of wax removed by the pig and the volume flow rates through the volumetric flow rates through the bypass. Finally, regarding the model improvements, we have expanded the user-defined functionality such that LedaFlow is now supporting solid deposition models. This can be used to implement your own model for solid deposition on the pipe wall, asphaltene or wax. We make the assumption that no solid particle will be transported in the fluid phases. If you enable that option, you will have specific variables added for pipes, like the custom deposition rate, the deposit layer thickness, and the total mass of custom deposit. Please note that we have decided in LedaFlow 2.10 to hide the UDF functionality by default. Before it was shown, as you can see here on this screenshot. So it was shown by default, but this is a quite advanced functionality. So we have decided to disable it by default, and it's possible to make it visible again through the user preferences. So we have made some great speed improvements in LedaFlow 2.10. The parallelization has been improved for slug capturing cases that are using the new solver. So it is now possible to use 8 or more CPU cores, while in previous versions of LedaFlow, we recommended to only use 4. In general, the calculation speed has also improved. And to demonstrate this, I'm going to take a test case here. As you can see, it's a test case that is run for 10 minutes. It represents a flow line of 20 kilometers, and it includes an end node separator. The flow line is discretized with 16,816 cells. And the case is initialized with a restart file so that slugging is already well established. You have here also the description of the laptop that is used for this specific test. So to explain you what we're trying to achieve, so what LedaFlow during the simulations divide computational calculations into parallel threads for faster processing. And what we do is that we analyze how the equations are evaluated and solved, and we target those with lower efficiency, and of course try to improve that efficiency to reduce the processing time. So the graph that you see here shows the simulation wall time that was achieved by LedaFlow 2.9. It is a bit difficult to look at this or to understand that graph. So if we look at it in a logarithmic scale, we can see the dotted line that you can see here. That's the ideal situation. That means that if we double the number of threads, we use half of the CPU time. This is an ideal situation, and as you can see, in reality, we tend to use more time than that. So the idea when we work on parallelization is to come as close as possible to this ideal situation here. So for this specific test case, the graph on the left-hand side shows the result of LedaFlow 2.9 and 2.10, and as you can see, we have managed to come closer to that ideal situation. If we look at the graph in the middle, we see that LedaFlow 2.10 is 7% faster than LedaFlow 2.9 when running with 2 parallel threads. It is 12% faster when running with 4 parallel threads and 20% faster when running with 8 parallel threads. In terms of efficiency, which is shown on the graph on the right-hand side, it means that we are now achieving a 60% efficiency in LedaFlow 2.10, while it was only 51% in LedaFlow 2.9. We have, of course, made the same comparison with a larger number of cases, and the conclusion is that LedaFlow 2.10 runs 10% faster than LedaFlow 2.9 when using 2 threads. And when we run with 8 threads in parallel, it will be 24% faster than the previous version. Another performance improvement that we have done is that we've made the loading of input files in interactive mode faster. So that is when you're using the scripting engine that is called Softshell. And we also have added a new function to the cases module that allows you to make visible the cases that are created in Softshell inside the user interface of LedaFlow Engineering. So that will probably speak to people who are using LedaFlow together with Resolve, because that's when you want to visualize simulation progress, for example, of your cases that are created in Resolve together with LedaFlow or in the LedaFlow user interface. Finally, I would like to mention one of several improvements regarding parametric study. It is now possible to duplicate a parametric study with no results. So this is of course faster than duplicating it with results, which was the only option in previous versions of LedaFlow. Also, when adding hidden cases to the case browser, parametric studies are now attached to their base case, which was not the case before. This is what I wanted to show you today. So we have now 10 minutes for questions, if you have any.